Welcome to Chapter 3, where we'll put theory into practice using Python. In this hands-on chapter, we'll simulate spin transport phenomena, from solving the spin diffusion equation to modeling complete GMR and TMR devices. By the end, you'll have working code that demonstrates the physics we learned in previous chapters. Here's what we'll build in this chapter. First, we'll create a numerical solver for the spin diffusion equation. Then we'll model spin accumulation at ferromagnet to non-magnet junctions. We'll build a complete spin valve class for GMR simulations. We'll simulate TMR bias voltage dependence. And finally, we'll implement magnetization dynamics with spin orbit torque. You'll need NumPy, SciPy, and Matplotlib installed. Let's start by solving the spin diffusion equation numerically. This is the fundamental equation governing spin transport in materials, and solving it will help us understand how spin signals decay with distance. We'll use the finite difference method to solve the spin diffusion equation. We discretize space into endpoints with spacing dx. The second derivative becomes a difference formula, creating a tridiagonal matrix system. The diagonal elements contain beta, which includes both diffusion and relaxation terms. Off-diagonal elements contain alpha from the diffusion term. We apply boundary conditions, fixed spin accumulation at the injection point and 0 at the far end. Running our solver for copper, we get this result. The numerical solution shown in blue follows the expected exponential decay profile of the finite domain solution shown in red dashed line. This validates our implementation. For copper with diffusion coefficient 0.01 square meters per second and relaxation time 10 picoseconds, we get a spin diffusion length of about 320 nanometers, in line with the roughly 350 nanometers measured for copper at room temperature. The code uses SciPy's banded solver for efficient tridiagonal matrix solving. Now let's model what happens when spin-polarized current crosses from a ferromagnet into a non-magnetic metal. This interface physics is crucial for understanding spin injection devices. At an FM-NM junction, spin accumulation follows different equations on each side. In the ferromagnet for x less than 0, accumulation decays toward the interface with short diffusion length. In the non-magnetic metal for x greater than 0, it decays away from the interface with longer diffusion length. The magnitude depends on spin polarization and current density. Continuity at the interface requires proper boundary matching. The simulation results show the characteristic asymmetric profile. On the left, the ferromagnetic permalloy region shows rapid decay over just 5 nanometers. On the right, the copper region shows much slower decay over 350 nanometers. The interface at x equals 0 shows the peak accumulation. This asymmetry reflects the different spin transport properties of ferromagnetic and non-magnetic materials. Now we'll build a complete spin valve simulator using object-oriented Python. This will let us calculate GMR characteristics, including the field-dependent resistance switching. Our spin valve class encapsulates all the physics. Attributes include resistances for both spin channels, coercive fields for free and pinned layers, exchange bias, and current magnetization states. The calculate resistance method computes resistance based on whether magnetizations are parallel or anti-parallel. The apply field method updates magnetization states by comparing the field to coercive thresholds. And the field sweep method simulates a complete hysteresis measurement. Running the simulation produces this characteristic spin valve curve. At high positive field, both layers are parallel, giving the low resistance parallel state. As the field decreases, the free layer switches first, creating the anti-parallel high resistance state. The pinned layer switches at higher negative field, returning to parallel state. The GMR ratio, shown in the title, quantifies the resistance change. Different coercive fields create the distinct switching events. Real MTJ devices show a voltage dependence of TMR that we should understand. Let's simulate how TMR changes with applied bias voltage. At zero bias, TMR reaches its maximum value given by the Joliet formula. But as bias increases, TMR decreases following an empirical parabolic dependence. The formula is TMR at bias V equals the zero bias TMR divided by 1 plus the square of V over V1 half. The characteristic voltage V1 half is typically 0.3 to 0.5 volts for magnesium oxide tunnel junctions. This decrease comes from magnon excitation and density of states effects at high voltage. The simulation shows the symmetric TMR versus bias curve. Peak TMR of about 90% occurs at zero bias for these parameters for this typical mid-range magnesium oxide junction. Record devices reach well over 600%, as we saw in Chapter 2. As voltage increases in either direction, TMR decreases following the parabolic model. At plus or minus 500 millivolts, TMR has dropped significantly. This behavior is important for device designers who need to optimize the trade-off between signal amplitude and operating voltage. Our final simulation tackles magnetization dynamics. We'll solve the Landau-Lifshitz-Gilbert equation with a spin-orbit torque term to see how SOT can switch magnetization. The LLG equation describes how magnetization precesses and relaxes. The first term gives precession around the effective field at a rate set by the gyromagnetic ratio gamma. The second term with damping alpha causes relaxation toward equilibrium. The SOT term adds a torque from spin current that can drive magnetization away from equilibrium. The cross products determine torque directions. We use SciPi's ODINT to solve this system of coupled differential equations. The comparison is dramatic. Without spin-orbit torque, on the left, the magnetization shows damped precession settling to equilibrium with its out-of-plane component staying positive. With spin-orbit torque, on the right, the torque drives the magnetization to switch. The out-of-plane component flips from positive to negative, demonstrating successful spin-orbit torque-induced switching. The switching occurs within a few nanoseconds. This is the physics behind SOT-MRAM technology. Here are tips for successful Spintronics simulations. First, ensure your device size is smaller than the spin diffusion length, or spin information will be lost. Second, include magnetization hysteresis in GMR and TMR calculations for realistic behavior. Third, the LLG equation is stiff, so choose appropriate ODE solvers with adaptive stepping. Finally, always validate your parameters against experimental data when possible. Let's review what we built. We solved the spin diffusion equation with finite differences and validated against analytical solutions. We modeled ferromagnet to non-magnet junction spin accumulation with asymmetric decay profiles. We created a spin valve class for complete GMR simulation. We simulated TMR bias voltage dependence. And we implemented simplified LLG dynamics with SOT-driven magnetization reorientation. You now have Python tools to explore Spintronics physics. This concludes Chapter 3, Learning Spin Transport with Python. You've gained hands-on experience simulating the physics from our earlier chapters. In Chapter 4, we'll see how these principles translate into real-world applications, from hard drives to MRAM to quantum computing. See you in the final chapter.